Hello, welcome to the video lecture series on contact mechanics in the course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work in the Division of Machine Elements at Luleå University of Technology. And this is the second part of the first video lecture on contact mechanics fundamentals, and it's about half-space theory. In this part, we will dive into the half-space theory. And we start with a point loading of a half-space. We will go through what happens if we have a distributed load on the half-space, and then what happens when we have the contact between two deformable bodies, and this will ultimately lead us to the Boussinesq deformation equation. So what we see here is a half space and a contact region with which is far away from the boundaries of that half space. And in the following we will focus on frictionless contact between two rough surfaces. And although we don't consider what stresses that develops beneath the surface, the so-called subsurface stresses, you will be able to actually model these with the theory you learn in this course. So let's imagine we have a point loading of an elastic half space. A force is pointed at a position x, y, and z equals 0. So due to this point load at the position x, y, z equals 0, we will have a subsurface stress field developing. And here we have denoted them at a certain point with distance ρ from the location of the acting force. And we also have a distance r, which is the horizontal distance, the distance in the xy plane to that point. And this will be of interest later on. So you also have a top view to see that the force is acting counter z direction, and that we have this radius to that point where we see the stresses sigma z and tau rz. Due to that point load, which we now denote by F1 because we're going to apply some more of those, we will have a deflection or deformation of the boundary surface of that half space. And this deformation will look something like what we have here on the red line. And at the distance r1 in the xy plane, we will see the deformation u1. So remember that this is now rotational symmetric. So everywhere on the radius r1 in the xy plane, we will have the same deformation, u1. It turns out that the relationship between the deformation u1 and the point force F1 will look like this. So it will involve the distance r1 from that point, and as we can see, as we move further away, the deformation will be smaller and smaller. We can also see as we move closer and closer to the point where the force is applied, this deformation will just continue to increase, and it will actually blow up at the actual point itself. G here is the shear modulus, nu is the Poisson ratio, and 1 over G is actually related to this expression involving both the Poisson ratio and the Young's elastic modulus. So we can write it in terms of the Young's elastic modulus like this. Let's now assume that we apply another point force in this half space, F2. Then at the radius R2, which is actually ending up at the same place as R1 did, we will see a very similar deformation or magnitude of deformation U2 as we saw for the force F1, which gave rise to U1. However, the reason for the similarity in this case is because we have, although we have a higher load, F2 is larger than F1, the radius R2 is also larger than R1, and therefore U2 and U1 are very similar. Again, they are related, U2 are related to F2 and R2 by the same expression as before. So now if we add these up, we get the total deflection looking like this. So if we measure it at the point, the same point as we measured U1 and U2 before, it will now look like this. And it's just the sum of those two terms. So that we can formulate it like this. We have this ratio involving the Poisson ratio and the Young's modulus, and then we have the sum over the F's over the R's. If we then add more and more point forces, we realize that we are approaching the situation where we instead have a distributed load, which we can think of as a pressure or normal stress acting over the surface. And well, if we consider the pressure acting over a small area, delta A, at this point xi, then the deformation will just be the sum of all those small forces, delta Fi, which equals Pi times delta A. Ri is just the Euclidean distance between the point x and xi in a vector notation. So x minus xi and y minus yi. And therefore we can write the deformation in terms of the pressure Pi as we see here. Now this is a discrete representation, and we all realize that if we make these delta A small enough, then we probably can approach the continuous form, which looks like this. And it tells us that the deformation in point x, y is a result from the pressure acting in all the points all over this half space, and those are denoted by x prime and y prime, and the contribution from each pressure in x prime, y prime points coming from the ratio between the pressure itself and the distance between this point x prime and y prime to the point x and y, where we are measuring the deformation. The pressure itself arises from the contact between the two bodies which are loaded against each other under a certain force. And the deformation may be different due to the elastic properties of the bodies. So here we see we have deformation U2 from the pressure P in the upper body, and we have U1 from the deformation U1 caused by the pressure P in the lower body. The total deflection is then of course just given by U1 plus U2. Nothing strange with that. And because of linearity of the deformation relation to the pressure, we can write the total deformation in a very similar way as we did before for the deformation for each of the bodies. Doing so, we introduce a reduced elastic modulus or effective elastic modulus if you like, and these may be introduced in different ways, and here we have two of them. 1 over E star, which is equal the sum of these Poisson ratio over Young's modulus type of terms, or we do 2 over E prime as a definition for this effective or reduced Young's modulus. E star is typically found in books devoted to contact mechanics, like for example the book by Kay and Johnson, while you find E prime in more tribology oriented writings or publications. I personally see an advantage with the latter one, because by taking 2 over E prime will be sort of the same magnitude as E1 and E2 if they would be the same, while E star would be approximately half of it. For steel, for example, we would have something like 210 gigapascals for the E prime if the E1 and E2 are of that order. The mathematical expression for the deformation and its relation to the pressure was actually found by Boussinesq and Cerruti independently at about the same time. You can see publication list down here is 1885 and 1882 for those works. And normally you find a Boussinesq problem being associated with a boundary value problem when it has prescribed normal tractions on the boundaries of the half spaces, and the Cerruti problem is identified as the one that belongs to tangential traction boundary conditions. Later on, Louve also was researching into this, and he summarized and, well, probably reinvented a lot of Boussinesq and Cerruti's works, and I've given you 2 references of Louve's papers here. So the expressions for the deformation that we have until now seen, they are the Boussinesq type, as they are produced by normal tractions acting on the frictionless planar boundary of the half spaces. Now we can summarize the deformation in both 2D and 3D by means of this convolution type of expression, where K can be referred to as a kernel function. And in 2D, in the contact mechanics problem in 2D, we have a 1D expression for the kernel, and this is given by the logarithm of the absolute value, or the distance between the point where the point load acts and the point where we evaluate the deformation. And for more details on that, you can take a look in Kay and Johnson's book. And then in 3D, the kernel looks like, yeah, precisely like we have seen before.